Okay, now that we've covered the 4 quantum numbers, we're going to be able to use those 4 quantum numbers to envision how electrons arrange themselves in atoms to make atomic structure. And when we do this, we'll gain some insight into why the periodic table is arranged the way it is. Now, before we do this, there's a couple rules that we want to go over that describes how electrons fill into shells in order to build the atomic structure. The first we're going to cover is the Aufbau Principle, which states that electrons are added into orbitals from lowest to highest energy. And we find the energies depend upon both N and L. So what happens is you fill the electrons into orbitals with the lowest values of N plus L. If there's a tie, then you're going to put it into the orbital with the lower value of N first. So let's do a couple examples just to see what I'm talking about here. Let's say we have a 1s orbital, and a 2s orbital, and a 2p orbital, and a 3s orbital, and a 3p orbital, and a 3d orbital, and a 4s orbital. To find the value of N for each of these orbitals, we just look at the number out in front. And so for this particular orbital, it's going to be N is 1, N is 2 for a 2s, N is 2 for a 2p, N is 3 for a 3s, it's 3 for a 3p, it's 3 for a 3d, and it's 4 for a 4s. Now to each of these orbitals, we're also going to add in the value of L for each orbital. An s orbital has a value of 0, so I'm going to go ahead and add in 0 for all of the s orbitals. P orbitals have the value of 1, so I'm going to add a 1 in for all p orbitals. And a d orbital has a value of L is 2. If I take this sum, a 1s orbital has a sum of N plus L as 1. A 2s is 2, 2p is 3, 3s is 3, 3p is 4, 3d is 5, and 4s is 4. So if I were to arrange these in order from lowest energy to highest energy in terms of N plus L, well, let's see, 1s is going to be first because that's the lowest value, and then 2s would be second. And now here we have a tie. We have a 2p orbital and a 3s orbital, which their sums of N plus L are both 3. Well, in this case, what we do is we take the orbital with the lower value of N between the two, which is the 2p, so that would be next, and then 3s comes next. Then these two orbitals here and here are the next highest values of N plus L. We're going to choose the 3p first because it has the lower value of N, so 3p, and then 4s, and then finally 3d of these orbitals would be the highest in terms of energy. So this is the basis of the Aufbau Principle. The second idea that we're going to need is called the Pauli Exclusion Principle. And this states that no two electrons in the same atom can have the same 4 quantum numbers. Let's see what this means. Let's say we have 2 electrons here, electron 1 and electron 2. And we're going to start to fill these electrons. Let's put them into our lowest energy orbital. That's what we're supposed to do with the Aufbau Principle. We're going to stick them into the 1s orbital. So if I have a 1s orbital, the principal quantum number for this orbital is going to be 1. The angular momentum quantum number is going to be 0, because that's true for all s orbitals. And the value for m sub L for this particular orbital is also going to be 0, because we remember that L is going to vary from negative L to L, and of course negative 0 to 0 is just 0. Then let's say with this particular electron, we're going to give it the spin value. You might remember spin values can be plus half or minus half. We'll give this one a spin of plus half, and we designate that by just sticking an arrow up in this line that represents a 1s orbital. Now, let's look at this particular electron. We can give this electron these same three quantum numbers here. We can give it n equal 1, L equals 0, m sub L equals 0. And we can do that because we can give this particular electron a spin of negative half, and we can designate that by drawing an arrow down in that direction. And we'll notice that these two electrons have three quantum numbers that are the same, but that fourth number is different. So electron 1 and electron 2 don't have all four quantum numbers identical. So this is valid. This is something we can do. Now we're going to take electron 3 and we're going to try to stick it into this orbital. Well, if we do that, we can make n equal 1. Well, we have to because that's this orbital. L's got to be 0. M sub L has to be 0. And our choices for m sub s are plus half or minus half. That's it. M sub s is either plus half or minus half. Well, if we give it plus half, we can't use it because that would violate the Pauli Exclusion principle, because electron 3 would have the same four quantum numbers as electron 1. And we also can't stick it spin down like this, m sub s negative half, because doing so would give electron 3 the same four quantum numbers as electron 2. And so we see that this particular orbital, a 1s orbital, can only have two electrons in it, one spin up and one spin down. And that actually turns out to be true of any particular orbital. In any particular orbital, you can only have two electrons in there. One's going to be spin up, one's going to be spin down, and that is because of this Pauli exclusion principle. Okay, the last rule we're going to cover is called Hund's rule, which says the most stable arrangement of electrons maximizes unpaired electrons, all with the same spin orientation. What in the world does that mean? Well, let's imagine we're going to start filling some electrons into a 2p subshell. So in a 2p subshell, let's see, this orbital would be a 2p, this orbital would be a 2p, this would be a 2p, and this would have an m sub L value of negative 1, this would have an m sub L value of 0, this would have an m sub L value of plus 1. So if we just look at this as orbital 1, orbital 2, orbital 3, they all have the same energy because they're all 2p electrons. They're all going to have the value of n as 2 because it's a 2p. L is going to be 1, and m sub L is going to vary for all of them. So orbital 1 is going to have m sub L is negative 1. Orbital 2, of course, will have n equal 2, L equal 1. M sub L for orbital 2 will be 0. And orbital 3, n will be 2, L will be 1, and m sub L will be plus 1. And now we're going to stick, let's say we're going to stick 3 electrons in, or maybe more. We'll just put 3 out here to begin with. And if I want to put this first electron in, I can stick it in this orbital here with its spin up. And if I do that, this particular electron has a value of n of 2, L of 1, m sub L of negative 1, and m sub s, that's going to be plus half because the electron's got to spin up. So we've taken care of electron number 1. Now we're going to stick in a second electron. And when I do this, there's a lot of different ways this can be done. I mean, I can't stick the electron in here, spin up, because that's going to violate the Pauli exclusion principle. If I did that, you'd have 2 electrons with these 4 quantum numbers. But I certainly could put the electron in this orbital, spin down. Then we'd have 2 electrons with, these 3 numbers would be the same, but this one would be different. I could also stick the electron in this orbital, spin up, in this orbital, spin up, in this orbital, spin down, or in this orbital, spin down. And Hund's rule is going to help us figure out what we need to do here. Now the first thing that Hund's rule is going to tell us is that we're going to want to put the electron in a different orbital than the one where we stuck the first one. And this is just like Coulomb's law. If you remember, two electrons having the same charge, they're going to want to repel each other. And when you stick two electrons in the same orbital, that's like sticking two electrons in the same space. And we know electrons don't want to do that on the basis of Coulomb's law. So the first thing we're going to do is we're going to stick the second electron in a different orbital. The second thing that we're going to do, according to Hund's rule, is we want to give those electrons the same spin orientation. So it really doesn't matter if I choose this orbital or this one, but what we are going to do is we're going to give it the same spin orientation. So that means we're going to try to align the spins first rather than pairing the spins like this. So that means I'm just going to go ahead and stick electron 2 in this orbital, spin up. So this electron would have the designation m sub s is plus half. When I stick electron 3 in, I don't want to stick it here because of Coulomb repulsion. I don't want to stick it here because of Coulomb repulsion. I want to stick it in this particular orbital, and I want to stick it in this orbital with the same spin orientation as the other two. So I'm going to place it here like that. We've taken care of that electron, and it's going to have a spin of plus half. Now if I'm going to stick a fourth electron in, it doesn't matter where it goes at this point. I'm just going to go ahead and stick it here, but we have to remember we're going to stick that one spin down. If I place in a fifth electron, that's going to go either here or here, it doesn't matter where. But I'm going to go ahead and place it in this particular orbital here. Of course, spin down. I can't put it spin up. That would violate the Pauli Exclusion principle. And if I stuck in a sixth electron, I could stick it in here. And at this point, I've filled this particular 2p subshell, because if I try to go put another electron in, I have to give that electron the same 4 quantum numbers as another electron that already exists in the orbital.